Thanks very much. Claire, take it away.
Perfect. Okay. Just share my screen quick. Can everyone see my screen? Great.
Yes.
In presentation mode?
Yes,
Okay.
you're fine.
Excellent, thank you. Well, thank you for having me. My name is Claire Trop, I'm an undergrad at Dartmouth. And for the last year or so, I've been studying traveling ionospheric disturbances, which Phil just gave an excellent explanation of, through Doppler-shifted AM radio transmissions. So I probably can't do in 2 minutes justice to what Phil just did, but basically we're talking again about buoyancy waves driven typically by geomagnetic activity, which are conveying and redistributing energy throughout the atmosphere. As I'm looking at tracking these disturbances, it's kind of thinking about why they're critical to be understood. So for the most part, it's energy transfer, and then also that large disturbances can interfere with technology such as GPS, and as you are all aware, radio transmissions in skywaves and such. So the motivation for this particular study was that a 2015 paper, also at Dartmouth, which successfully identified a TID using Doppler-shifted signals. But that study was somewhat incomplete in that it found a discrepancy between the phase velocity of the tracked TID and the GPS total electron content maps, which are often used to study these disturbances. So our current study has a much larger network, more advanced analysis, and most importantly, a much larger set of events to kind of continue confirming the capabilities of the technique. And also now we're working on kind of identifying further applications. And then of course, we're also trying to resolve the discrepancy which the original study originally saw in phase velocities. So this is our new network. It's 5 stations centered around the 810 kilohertz station in Schenectady, New York, the AM radio in the lower end of the AM band. We also have a station right at Schenectady to make sure that we're aware of any changes in the ground wave from the station, so we can factor those out and be sure that all disturbances we're seeing are actually from the changing of the F2 layer and not from the station itself. So notably, these red dots are marking our reflection points. We're just using a kind of a specular reflection model right now at the halfway point. That's where we're assuming our signal is reflecting. And the mechanism that we're trying to approximate here is that there's the signal coming from Schenectady, and as a TID goes by and the F2 layer moves up and down, the signal gets reflected off the bottom, and you see a Doppler shift if that layer is not stationary. Okay, so for instrumentation, there was actually a talk about this instrumentation at HamSci last year by David McGaw, which goes into much more detail of the actual technology, but the important things to note are that we're using, GPS timing on all of our receivers and a Raspberry Pi to do all of the frequency calculations. And on the left here, you can actually see one of the antennas this is the one in Schenectady, I believe. The kind of notable thing about our instrumentation and about our entire setup is that it's really cheap. You're using the infrastructure of the AM radio and then just setting up these receivers like in people's backyards, and through that we're able to do fairly sophisticated monitoring of the ionosphere. So we only have our 5 receivers set up, but in theory this is a method that could be expanded across the entire country for very low startup costs. So I'm now going to walk through kind of the methodology of a single day and how we go about tracking a TID and what that looks like. And I'll just use this day in July to kind of go through piece by piece. So the top is the raw spectrogram of the signal being reflected. And the box is the area where we're seeing a nice sinusoidal image in the reflection, and we're able to look at that for the tracking. The tracking is for this particular frequency is a semi-automated system, which I've overlaid on the bottom plot so you can see exactly what we're working with. And then just one last note, the red on the bottom, as I mentioned, there's a receiver at the 810 kilohertz station, and we've used that here to actually remove the natural oscillation of the 810 station and confirm that this is just Doppler shift from the skywave that we're looking at. So once we've identified a TID, we do a sliding normalized cross correlation between a reference station, and we use the same reference station for all, and each of the other stations. And we look for the region in the day that has a stationary lag and a stationary cross correlation with good normalization, like a high value for the cross correlation. Why we're doing this is we want a stationary waveform over the period that we're looking, so that we can do some analysis on the TID itself. And then a high dark red, as you can see here, correlation implies that the signals are very similar, and so it's basically not a fluke that they're giving a stationary lag. And so the next step is to consider the lags over that region and try to figure out the phase velocity and the wavelength and the direction of propagation. So on the left here, I have a geographic map, which is just plotting the lags at the reflection points, so you can get a sense of the geographic distribution of how the wave is moving in time, or in space, excuse me. So the red precedes the blue color. So you can see that this wave, just from looking without any sort of analysis, is moving somewhat southeast. And then we actually do two different methods for calculating the phase velocity and the direction. The first is a sinusoidal mapping method, where basically you fit each of the reflection points onto a circle around the transmitter, and then each of the reflection points gets a radian value and a lag value, which you can plot and fit a sine wave, and then you can actually get the phase velocity and direction from the characteristics of that sine wave, like the amplitude and the phase. And then another method we use is looking more specifically at phase velocities and the like k vector, like your phase velocity is being like omega over k. So you have to invert the lag and the distance and do some averaging. And I do this with every combination of 3, and you can get an average phase velocity and direction from that method as well. So two different methods to both confirm the phase velocity, wavelength, and direction. And so for this particular date, it's 300 meters per second, a 770 kilometer wavelength, and a southeast direction. So now that you've seen a little, and then the last piece, excuse me, is the auroral sourcing. So this doesn't apply for every day, but for the ones where there is a significant auroral electrojet index, AE index value, we can often identify an event initiation, a peak in that in the AE index, and then look at magnetometer data around Canada and the northern United States in order to try to identify where the magnetic disturbance may have occurred, which then spawned our wave that we're seeing at the red star down in the New York area. And then you can also do some little checks here about the phase velocity that we found and the distance from the source to the receivers, and if that propagation speed roughly makes sense with the initiation timing as kind of a check for the values that our methods produced. So this is the summary of our event data so far, our particularly exceptional events. For the last year, we're still collecting data currently, and so this table continues to grow. But as you can see, we have, I believe it's 13 different events from March to January, which we got a phase velocity from the 810 station in a direction. For some of them, the ones in bold, we were able to source an auroral cause. And then we also have been comparing our phase velocities with the GPS total electron content values. So I'm going to actually show an example of that to give a little bit more information. For this 926 day in September, it was an auroral day with actually 2 wave fronts, but we're going to focus on the primary one, which had a 430 meters per second south propagation. So This is a keogram, which is a way of looking at GPS data. It's basically a slit camera. So you're looking at a small range of longitude and over a fairly 20-degree latitude range, and then you're looking at how that evolves in time. And so you can see like there's an where this convenient arrow is, there's an angled increase in the electron content, which tells you that something is moving because it's changing location with time. And so this actually corresponds to a 430 meters per second south velocity, and then we can corroborate that with our 406 meters per second, also south velocity. And so that's a nice confirmation. Just to briefly go back to this slide, I will note that not every single GPS day perfectly matches as this one does, but in general, we see a really good correlation between direction, if not magnitude of the phase velocities between our two methods. Some other things we've been looking at and have been able to see on our data are these Terminator features. So this is actually a higher frequency station. It's 1560 kilohertz out of New York City. And we have been able on this station in particular to see the dawn and dusk Terminator features. These are also sometimes called like, I think like excursions or like from the norm at these times, but there are some papers I've cited here that you can read a little bit more about if you're curious. But basically what we did is looking at an RMS of the entire day over the whole, so I ran my automated tracker on the 1560 station for the whole year, and then did an RMS analysis of the velocity of the ionosphere moving up and down, and particularly focusing on the dawn terminator. So when the sun is rising, you can see on the year-long RMS spectrogram on the right here that there's like a really dark curve at the top and a similar but slightly less pronounced one at the bottom. And what that is showing is actually the occurrence of this excursion, this dawn terminator feature. And you can see that it actually is a seasonal dependence. So this, I should have said at the beginning, this is a purely nighttime technique because of when you can reflect off the F layer. And so when the night is really short, say in the summer, you see that the dawn terminator occurs much earlier in the evening, and or much earlier, and then later in the year, like in December, it actually ends up going off because we weren't collecting data for a long enough period. And so this seasonal dependence has actually allowed us to figure out a little bit about what these Terminator features are. And we believe that they're indicative of a photochemical source. So as the sun is rising, you get like ionization, and that causes the F2 layer to expand, which we would see as a downward shift in the Doppler because the layer is moving towards us. And so the signal is reflected upwards, like up here as in a positive Doppler shift. And so that's what we think is being explained, that we think is the explanation for this feature that we're often seeing, but it's interesting to note that there are other things other than TIDs that we can see with this method. And then kind of just a last note is that something we're currently working on and curious about is the difference between the lower half of the AM band and the higher half. So this is 810 kilohertz, 1080, and then 1560 respectively going down. And you can see that there's for the higher frequency transmissions, these are coming out of Connecticut and New York, that you get much higher amplitude Doppler shifts, a larger number of periods, and you also get many more frequent events. And this may be due to the change in reflection height between 810, which is going to reflect at a lower height in the ionosphere, and the 1560, which reflects much higher. We're still looking into this a little bit, but I think that in considering the method, this particular method is something to expand, it's important to note that potentially using the 1560 or the 810, something in the higher end of the AM band, would potentially be more effective for actually tracking these TIDs. So just brief conclusions. We've succeeded in identifying TIDs using Doppler-shifted AM radio transmissions, really confirming what Chilcote originally put forward as this method. In most of our cases, we find that the direction of propagation agrees with other established TID tracking methods like the GPS total electron content maps. The magnitude, we are seeing some discrepancies still, and we're still looking into that. We can identify auroral sources for TIDs in some cases, in particular the ones where there has been high AE index that day. There seems to be a seasonal dependence of the Terminator features at dawn and dusk, which characterizes them as products of photochemistry. And so that just kind of goes to show that this method is seeing other things beyond TIDs, and there's plenty to explore with this method. And then finally, that higher sounding frequencies, the top half of the AM band, create clear Doppler shifts for analysis. And so considering that in the context of this technique is something going forward that we are still working with. Thank you.
All right, fantastic. Thank you, Claire. Any questions from the chat that I'm missing? Please feel free to unmute if you're on the panelist side or restate in the chat.
I could ask one quick one, maybe. Claire, might be worth talking a little bit about that point you just made about the edge of the bands, right? The difference between the lower and the higher part of the band. There may be some physics, we think, right, buried just in that conclusion alone.
Yeah, so there's kind of two pieces that we're considering. One is that just higher frequencies reflect at higher heights, as I mentioned, and so potentially the change in altitude could be indicative of different TID behavior at different altitudes. And then another piece that we're also considering is, so I think as Phil mentioned briefly in his talk, actually, as you go to higher altitudes, the amplitude of your disturbances increase. It's part of like energy conservation. And so that could simply be a function of you're seeing the same activity, but you're just seeing it bigger, basically. And so it's easier to see because you're seeing a bigger movement of the ionosphere.
Thanks.
All right. Thanks very much. Possible that other questions will turn up in the chat, but in the meantime, you're getting a lot of well-deserved kudos. It is 3:20, so let's hand the mic over to Diego.